and everything. Okay, so let's start now. First, recall a bit what we have learned previously. Work. How do you define work? Work done. When I pushed a wall, no matter how hard I push the wall is not moving. It stays at rest. So there's no displacement, but there's force. You got force, you got no displacement. No work is done. No matter how hard you apply, how great is the force, still there will no work done. Okay, work is not done. Now, another scenario, let's say, imagine the earth moves around the sun. It goes around the sun. The force of attraction is acting on the earth and it tries to pull the earth towards the sun. But due to whatever reason that the earth does not go here, but instead it goes around the sun like this. So there is a displacement. In this case, it is a circle. And again, there is force. Where is the direction of the force acting? The direction of the force is acting, pointing to the center of the sun, okay? Because the sun is exerting the gravitational force on the earth. It tries to pull, but the displacement is not produced by this force, okay? So if the displacement is not produced by this force, then we said that this force is doing no work on the object. For work to be done, there has to be a force and there has to be a displacement in the direction, or rather in the line of the force. Why we don't say in the direction, later I will let you know. Okay, we say that for work to be done, there's a force and displacement in line with the force. So in the case of the earth rotating around the sun, there's no work done. The sun is not doing any work on the earth. Okay, because the force and the displacement is not the same direction. The displacement is not produced by the force. It is produced by other forces that causes it to go around the sun. So one more example, take an inclined slope like this. If you put an object on it and then it slides down like this, there's a reaction produced on the object. The object is here. So the reaction produced on the object is what direction? Perpendicular to the slope, right? Perpendicular to the sloping disk surface. Is the reaction doing any work on the object? I place the object here. Is the reaction force doing any work on the object? Now, the object slides down. It does not lift. It goes in this direction. So the direction of the displacement is parallel to the slope, to the floor, right? To the surface. It's not coming here. So there's no displacement here. Again, the reaction does not produce any displacement. There is a displacement down, but that displacement is not produced by the reaction. It is produced by other forces like the mg. So we say that the reaction is not doing any work because there's a force, but there's no displacement in the same direction as that reaction force. So reaction is not doing any work. Who is doing the work then? Object slides down. Who is doing the work? We see the force. Who is producing the force that pulls the object down? The gravity, the weight, the mg. So the way you say it is that either you say the name of the force or you say the agent that is producing the force. Meaning that I can say the weight is doing the work, or I can say the earth is doing the work, because this force is produced by the earth. So the earth is the agent that produces the force. Okay, be very clear. Work done, who is doing the work? The weight, you can say the name of the force, or you say the agent, the earth is producing, that is producing the force. So the earth is doing the work on what? The earth is doing the work on the object. So the object produces a displacement in the direction of this force. Okay, now mg, of course, in this case, you have to resolve the mg along the plane that is the force that is doing the displacement. So to define work done, we said as simple as it can be, we can say that W equals to force times into displacement. And this is in the line of force, meaning that the force and the displacement, they can be in the same direction or they can be in opposite direction. Now, in some cases where you have the force in the same direction as the distance, so that produces acceleration, right? In some other cases, you can have force is opposite to the displacement, like this. In what scenario, in what situation you can think of? You can think of a car braking. When a car brakes, there's a force produced in the brake pedal that opposes the motion. Initially, the car is moving to the right, and then the braking force acting to the left. The moment you step the brake, it does not stop immediately, right? It slows down and then it takes some time to come to rest, meaning that there's still displacement travel. There's still displacement to the right. And that is the S here, and the displacement direction during the braking duration is opposite to the force direction. This is where you get opposite force direction with the distance. Okay, so two cases here. That's why we don't say that force in the same direction as the distance, because force can be in opposite direction. So the correct word to use is in the line of the force, but you have to make sure that they are in line. So if one force is not in line, for example, like this, F, and then there's a displacement in this direction, then you have to do the resolving. The angle here, 20, any angle, you resolve F cos 20 times into the displacement, then you get the work done. This one, if the force is in the same direction as the distance, then we say that it is positive work being done. And if the force is different direction, then negative work is being done. And later we'll go more into detail what is positive work and negative work and how does it relate to the energy concept. Okay, now work done, again, in most of the examples, all the examples given, usually they will give you constant force, right? The force is constant. So when I push a box with a constant force of 5 Newton, then it creates displacement. We just put in the formula F equals to F times S. This take one value. What if the force is a variable? If I varies the force such that it increases and it decreases like this, I can put it on a graph where the force over a time period, or I can say over a distance, F against S, I get something like a bell curve. So the forces increases, peaks, and then drops. We get a variable force. What value do I put in the formula in this case? There's no fixed value, right? Because it keeps changing. So in a non-constant force, how do we find the work done? We take the area of the graph. So same, we take W equals to F times S. That is the area under the curve. Okay, so for a non-constant force, we calculate the area under the curve. How do we calculate the area? Do we use integration? No, we don't do integration in physics. That is the other maths. Okay, so to calculate the area of the graph, we use two methods. First, you can use the triangle. You can draw a triangle from the peak. Now, make sure when you draw the triangle, right, make sure you cut out the same amount of areas. So for example, if I draw until here, you can see that I'm cutting out this area this area over here, and this area has to be almost the same as this area. Same here. If I draw a triangle, one line here, this area must be almost the same as this area, so that the effect is cancelled out. And I can get the most accurate estimation. This is the first way you can do this. Calculate the area under the triangle. Okay. Second way, if it's impossible to draw a triangle, for example, like you get a weird shape, you get something like this. Okay, then how do you calculate the area? You use the square, calculate the grid. What is the area of one small grid, one small square, and then you calculate how many squares is completely covered by the body of the shapes here. Okay, so two ways to get the area. Now, so that is work. We are done with work done. This is just the basic definition of work done. Comes to energy. Okay, energy, and how does energy related to work? You see, energy, simply put, it is the capacity to do work. When you wake up in the morning, you feel excited, your energy level is high, and you tend to do a lot of things. You want to do this, you want to do that. Okay, so when your energy level is high, what happens? Your tendency to do things increases. You tend to do more things, so you tend to do more work. That's why we define energy as your capacity to do work. But that is in real life. In physics, in the context of physics, work has its specific meaning, which is force and displacement. So if I say an object has energy, meaning that that object has the capacity to do, either it can create a force or it can create a displacement. Think of this as a moving body traveling in this direction. I put my hand here and I try to stop it. Now, when it hits my hand, it applies a force on my hand and it pushes a few distance backwards. So there's force produced, there's distance. So there's work done. This object moving here strikes my hand is doing work on my hand here. Another case, same object, put it here, not moving. And then I put my hand here just beside it. Is it pushing my hand? It's not pushing. Just resting here, I put my hand here, but it's not pushing. So there's no force applied, there's no distance applied. Now, the first object, the one that is moving, is doing work on my hand. It can produce displacement and force. The second object that is at rest is not doing anything. It's not doing work. What is the difference between the first one and the second one? It's the same pen, it's the same object, it's the same hand, everything is the same. But how come the first one is doing work, the second one is not doing work? The answer lies in the state of the object. The state. The first object is in a moving state. The second object is in a resting state. So the state of the object tells you the capacity to do work. The state of the object tells you whether that object has energy or not. In this case, what is this energy? Kinetic, the energy due to the state of motion. That's why we define it as energy due to motion. Another example, I put the object on a turbine blade. This is the turbine blade, one of the blade. Okay, let's say I drop a ball. I drop a ball from 10 meters high. I drop the ball and then it strikes this plate, this blade, and it turns one revolution. Again, there is force produced, there is displacement in circular. Okay. Now, another case, I take the same ball. Now I just place it on the blade like this. I'm not dropping it from a certain height. I just place it here. Is it pushing it? No, it's not pushing it. It's just resting on the plate, on the blade. So it's not doing any work. It's not producing any force distance. It has no capacity to do work. What's the difference again? The first case, the first object and the second object. What's the difference? It's the same turbine blade, it's the same ball. The difference lies in the, again, the state in terms of the position of the object. One is at higher up, one is at lower, at the bottom, okay? The position in a uniform field, a gravitational field. Okay, so one is due to motion, that's kinetic, right? And another one is due to position. We define that as potential energy. So you have kinetic, potential energy, and they are the measurement of the capacity of an object to produce force or displacement. Okay, now talking about energy and the relation of energy with work. You see, when I rub my hand like this, I'm producing what? I'm producing force and I'm producing distance. So I do this, I'm doing work. And my hands got heated up. It becomes warm. Let's say I have done 20 joules of work by rubbing my hand like this. 20 joules of work I've done, that is the work done, right? So where does the 20 joules come from? Comes from my body, from chemical energy. So I've converted 20 joules of chemical energy to 20 joules of heat energy. And what happened to the energy here? Does it stay here? No. Does it get destroyed? No. Because energy, what is the law of energy? Cannot be destroyed, cannot be created. So I'm not creating energy either. The chemical energy from my body is from the food I eat. The food is from the light energy, photosynthesis. Everything can be traced back to the sun. So without the sun, technically the world would not exist. Okay, so energy is transformed from one form to another form. So here I'm doing this, chemical energy changed to heat, and then this heat energy doesn't stay here, it got dissipated into the atmosphere, and it stays in the atmosphere forever. Okay, it stays in the atmosphere, it doesn't get destroyed, it just stays there. So why are we having energy deficit? Because all the energy eventually turns into heat, and when it turns into heat, it cannot be recovered. That is why we are having energy deficit. Because many people say, why, based on the law of conservation of energy, energy cannot be destroyed? How come we are still facing energy deficit? Because of the heat energy that is cannot be recovered back, cannot be converted back into useful energy. Okay, so now by doing this action, I have done 20 joules of work, and then the energy storage, the energy of my body minus 20 joule, and the energy of the atmosphere plus 20 joule, because 20 joules has been added as heat. So the difference between work done and energy, listen, work done is the process. Energy is the storage. My body has minus 20, that's a storage. So the storage has decreased. Chemical energy minus 20. The atmosphere has plus 20. So that storage increases, and that process, the 20 joules going from my body to the atmosphere, that is work done. That is the relationship between energy and work done. Work done is the process of a conversion. Energy is the storage in one particular body. It goes to the next body. Okay. Now, talking about energy, work, most important is the one, the conservation of mechanical energy and also the work energy concept. Right, we will understand the conservation of mechanical energy first. So conservation of ME. Now, I throw a ball, I'm giving it at an initial velocity. The initial velocity very large, and as the ball goes up, the velocity decreases because there's an acceleration to the downside. So decreases, decreases, decreases. At the top, it is 0. At every point along the journey, the velocity changes and the kinetic energy changes. At the same time, the ball is gaining height. So the height changes and the potential energy also changes. There is a change in the two energy source, potential, kinetic. Here, we are going to neglect air resistance. So no air resistance, no external force. So this action, every pointer, if you look at the mechanical energy, starting at the bottom, I give it kinetic energy of 100 joule. The potential energy is 0 joule. Up here, potential energy is 100. Kinetic energy becomes 0 because it is at rest up here. If you take any point along the journey, let's say I take here, kinetic energy, okay, maybe it's 75, and then potential energy is 25. Halfway, midway, kinetic energy 50, potential energy 50 joule, 50 joule, 25 joule. Any point, you take the mechanical energy. Now, what is mechanical energy? Mechanical energy is the combination of Ke and Pe. Okay, it's the combination of K and Pe. So mechanical energy at this particular instance is 100 plus 0, 100. This is 75 plus 25, 100. 50, 50, also 100. And this one also 100. So in the absence of external force, the mechanical energy is always conserved. This is the first point that you need to remember. In the absence of external force, mechanical energy is conserved. We are not talking about kinetic. We are not talking about potential. We are talking about the combination of two. Stays the same. Okay, so 100, 100, 100, 100. That is why we use the formula kinetic energy at the bottom is the same as potential energy at the top. 100, 100. Eventually, it all gets transferred, 100% gets transferred to the potential energy, right? So we can write Ke loss. This is probably already familiar with this one, right? Ke loss is equals to Pe gain. And this expression focuses on the two extremes. From here, the lower boundary, go to the upper boundary, not in the middle. Okay, we are focusing on the two extremes where the kinetic energy loss all goes to potential energy gain. So here I can write half mv squared equals to mg h. And using this equation, you can calculate, as you have done in the previous exercises, you can calculate the height reached if I throw it, or you can calculate the velocity at the ground if I drop it. I don't have to put the mass because the mass can cancel out. So I can get another one, half v squared equals to gh. This equation, they are based on what is the principle behind it? What is the meaning behind this equation? Is that mechanical energy is conserved. If mechanical energy is not conserved, then we cannot use this too. And later I'll show you examples of mechanical energy not conserved in the presence of external forces. Okay, so here we have understood that conservation of mechanical energy, that only happens in the absence of external force. So no external force, no external force. All right, okay. Now we go into the work energy concept. Okay, the work energy concept. Now suppose that there is a car traveling at velocity u. Okay, it may be traveling, it may be at rest. Okay, so it's moving, and the force that propels the car comes from the engine. So I label this Fe, engine, and then the car has a displacement S After a certain period of time, it has a final velocity v. Calculate the work done. W equals to force times into displacement. What is this force? This force is the engine force. So who is doing the work here? The engine is doing the work. Okay, the engine is doing the work on the car. Is the engine doing positive work or negative work? Same direction. You see the force, same direction as the distance. So it is doing positive work. Okay, now F, we know that that's MAS. Acceleration, okay, using our Szilard equation, v squared equals to u squared plus 2as. So we express a in terms of all others. So v squared minus u squared divided by 2s, that is my a. Put it in, I get m v squared minus u squared, 2s and an s. The s got cancelled out and I factorize the 2 out. So I get 1 over 2 m v squared minus u squared. And this one, expand the bracket, I get half mv squared minus half mu squared. What is this? This one is final kinetic energy. So I write KEF minus initial kinetic energy. So final, you minus initial, we get the change. I continue here. Change in kinetic energy, that is equals to work. This is the work energy concept. Do you need to remember the derivation? Answer is yes, because sometimes in the past years, they will ask you to show it or to prove it. So you need to know how to derive this. The work energy concept. So what does the work energy concept say? This W equals to change in kinetic energy means that when you do work on a body, that body is going to gain certain amount of kinetic energy, not potential. We are not discussing potential here. The body is going to gain kinetic energy that is based on how much work you done on it. Okay, now this one, I'm doing, the engine is doing positive work, right? Positive work means that I'm adding energy in. Okay, so positive work means that I add kinetic energy using, based on the energy concept. If I do positive work, I'm adding kinetic energy. If I do negative work, then I'm removing kinetic energy. So the engine is doing positive work, is adding kinetic energy. So the car accelerate and the velocity of the car here higher than here. So it has gained kinetic energy. How much gain? You calculate Fe times into S, then you get how much increase in the kinetic energy. So suddenly, if the brakes are pressed, okay, so the driver presses the brakes and then there's a force, net force created opposite to the motion. Brake. Okay, so the engine force now disappear and the brakes are pressed. There's a net force to the left and there will be a deceleration. Still, it moves a certain distance to the right. So during this time, the brakes is doing the work, right? The brakes is doing the work. It is doing negative work on the car because different direction. So if it's doing negative work, then what happened to the car? It loses kinetic energy because negative work means what? Removing kinetic energy, right? So the engine accelerates the car, giving it kinetic energy, and then the brakes decelerate the car and takes away the kinetic energy, and eventually the car comes to stop and KE becomes 0. Okay, so what happened when the car moves at constant velocity? You see, here, the car traveling at constant velocity, meaning that we have engine force, let's say 50 Newton to the right, and then we have a resistive force, 50 Newton to the left, constant V. Okay, constant V, what happened to the kinetic energy? Does it change? It does not change. It remains the same. Okay, constant. Now, why there's no change in kinetic energy? You see, there are two forces here. One is doing positive work, one is doing negative work. Where is the displacement? Displacement is to the right, S. So the engine is doing positive work. The brakes or the resistive force, the air resistance, they are doing negative work. So while the engine is adding the kinetic energy, 10 joule, 10 joule, 10 joule, then the resistive force is taking away. Take 10 joule, take 10 joule, take 10 joule. So the net result, the net work done on this body, on the car, is 0. So there's no change in kinetic energy, and the car remain at constant velocity. Okay, so this one is adding this amount of energy, this one is taking away this amount of energy. That's why there's no increase in kinetic energy, and the car moves at constant velocity. All this, they are based on the work energy concept. Okay, so in short, we can say work done on the body is equals to the change in kinetic energy on the body. Okay, now you see the one that is doing the positive work, the engine is doing the positive work, meaning that it is adding the energy in, right? Where is it taking the energy from? It's taking the energy from the combustions, right, in the engine, the working of the engine, mechanical energy from inside the engine changes to the kinetic energy of the car. And then the drag, the resistive force, takes the kinetic energy and it changes to what? Eventually, it has to go somewhere else, right? You cannot just destroy it. So the energy goes to the heat energy in the tires with the air resistance and also the sound energy, all this. So still, it obeys the conservation of energy. Okay, the work energy concept still obeys the conservation of energy. That energy cannot be destroyed. So it doesn't mean that I'm removing the KE is just disappear, got destroyed. No, it goes to somewhere else. Okay. Okay, now let me raise this, get some space. Okay, another example is, you can think of it like a ball that is being raised at constant velocity. Suppose that I raise the ball, so I'm producing a force, this is applied force, at constant velocity. So if constant velocity means that the forces are balanced, right? What are the forces here? There's applied force up and there's mg downward. These two forces are balanced. Again, very similar to the car. I'm doing positive work. I raise it. The displacement is up. So I'm doing positive. I'm adding kinetic energy. There's a change in kinetic energy to the ball. At the same time, because the mg has the same magnitude as my force, so it is taking away the same amount of energy from the ball, right? So it's taking away the same amount of energy, and as a result, the ball does not gain any kinetic energy, so it moves at constant speed. Now, where does the energy go? The mg, which is the Earth, is doing the work. The Earth is trying to pull it down, right? So the Earth is doing the negative work on the ball. It is removing the kinetic energy that I added. It is removing it and it converts it to what? To potential energy. That is why you have the ball moving at constant V, no change in kinetic energy, because all the increase in kinetic energy has gone to the potential energy here. So up here, it has gained potential energy equals to mgh, like this. Okay, so this one, I'm doing positive, the earth is doing negative. I can say in the sentence, often you will see this sentence, it says that the applied force, which is the force that I apply, is doing work against gravity. Okay, if I'm doing positive work, the gravity is doing negative work, I can say it like I'm doing work against gravity. Okay, I'm doing work against gravity. In the case of the car, the engine is doing work against the resistive force. Okay, the engine is doing work against the resistive force. Okay, another question. Is the mechanical energy conserved here? Okay, this is very important. Now, is the mechanical energy conserved? Again, mechanical energy is potential plus kinetic. Understand that the work energy concept does not discuss whether mechanical energy is conserved or not. It only tells you how much Ke will the object gain if you do this much of work. Based on the formula here, we already have, right? You can even calculate. When I do this much work, it tells you how much Ke will gain for that particular object. This is what the work energy tells you. It does not discuss anything about the conservation of mechanical energy. If you want to analyze the conservation of mechanical energy, you have to look at systems. You have to look at external forces. Okay, systems and external forces. That's when conservative and non-conservative forces comes in to the picture. Okay, now first, next one here, we will understand the change in the mechanical energy. All right, so let's talk about external forces first. External forces, in all the examples that I'm going to show you, and also in this part, the energy, work, and power, all the examples that we are going to take Earth and the body system. Again, stick with me. Earth, body, or the Earth ball system. In this case, Earth ball system. If I take the Earth and the ball as my system, remember, what is a system? A system can have many bodies, right? So if one body exerts a force on another body, what is that force? That force is an internal force. When one body inside the system exerts a force on another body inside the system, that force is not external. So if I take Earth and the ball as a system, is the gravity external? The gravity is not external, because the gravity is exerted by the Earth, and Earth is a member of the system, so the gravity is not an external force based on my Earth ball system. Okay, so gravity is not external, or I can say that gravity is a conservative force, not external. External force can change the mechanical energy of the system. Like this ball, remember this one we discussed earlier? This one, why the mechanical energy all can be the same, 100, 100, 100, 100, because there's no external force, right? This ball, I throw it up, there's gravity acting, still it's 100, 100, 100, 100, because gravity cannot increase or decrease mechanical energy. Okay, it stays the same, 100, 100, 100. So mechanical energy stays conserved. So gravity is a conservative force. Now, what are the examples of a non-conservative force? Non-conservative force is anything that is other than the earth ball forces, frictions, that is outside of my earth ball system. Engine force, that is also an external force, because engine force, suddenly it can accelerate the body. Imagine like this ball, right? If I throw it up, it's moving, it has no power to accelerate by itself. But if this thing has an engine, like a propulsion system, it can accelerate itself. So that is why the engine is external force. Okay, so engine force is external, resistance is external. What else? Applied force, any push or pull by a person. So I write it down here. External force, external, engine, resistive, or it can be applied force. Okay, so external forces, they are non-conservative forces, meaning that they can change the mechanical energy of the system. They can either increase the kinetic or the potential. So the mechanical energy is not conserved. Okay, let me show you one example. We take the same example here. Now, what we understand here, we understand that there's external force can change the mechanical energy, right? So let's take the same example here. By the way, if you experience lagging, let me know in the chat. I also have this recorded down. If there's any lagging, I will post it in the group. Okay, back to here. So we take this example. Now, we take 2 points. One point is at the bottom here, point A, here, up here. We have an applied force acting on the ball. Is this external or internal? This applied force is an external applied force, meaning that this applied force can change the mechanical energy. It can increase the mechanical energy. Okay, what is the mechanical energy at point A? PE 0, considering it starts from the ground. KE 0. So the mechanical energy is 0 also. It's the sum of the two. Huh? Up here at B, what is the PE? MGH. What is the KE? 0. What is the mechanical energy? MGH plus 0, that's MGH. So compare the mechanical energy at these 2 points. Are they the same? They're not the same, meaning that it has increased. It is not conserved anymore. Not like this one, 100, 100, 100, 100. Here it has increased. Why it has increased? Because there is applied force. That's external. That is non-conservative. So it can change the mechanical energy of the system. This is my system, the earth ball system. Okay, now erase this first. So what we have understood so far, that work, if you have external work, okay, you see, if you have external work, what is external work? The work done by external force, this applied force. Okay, the work done by the gravity is not external. So we only consider the external. We are only looking at the external forces that is doing the work. So this applied force is external, and it is the only external, right? There's no other external, considering that the resistance is negligible. So the only external force here is the applied force. So the applied force becomes the net external work. Okay, the applied force is doing a net external work, and that produces an increase in the mechanical energy. Here we have another expression. This tells you the conservation of mechanical energy. And how do I know whether it's conserved or not conserved? We look at the external forces. This is not the same as work energy concept. What is the work energy? With work energy, we don't care about the external forces. We only care about one particular body. If I exert a force, the kinetic energy will change. If I exert another force, the kinetic energy will change. I don't care whether it is external or internal. Okay, and it doesn't tell me whether mechanical energy conserve or not. But this one up here, external force doing the work will have a change in mechanical energy. So change in mechanical energy, either PE or KE. And this external work must be the net. Okay, must be the net. Because in some cases, like you have friction, so meaning that you have more than one external forces. I push, there's applied force, and there's air friction. There are two external forces. You calculate the net force. The net force is the one that increases the mechanical energy. That's why I put here net. Okay, understand that this external must be a net external force. Okay, so just to summarize a bit, no external force, no external force, mechanical energy is conserved. So like this one, 100, 100, 100, 100. If there's external force, mechanical energy is increase or decrease. There's a change. That is summarizes all here. Okay, now we will go to the next one. I will show you a few examples so that you can fully grasp the concept here. Now, let me erase this. You want to screenshot this, you can screenshot. I want to erase this. Excuse me. Right. Okay, first example. A ball of mass 50 grams is thrown vertically upwards from ground level with a speed of 30. Find the maximum height to which it rises, taking G as 9.81. Okay, so A, first, is the mechanical energy conserved or not conserved? You see, a ball is thrown vertically upwards. So here, going up like this. It's thrown, meaning that I'm applying a force, right? I throw it up, there's a force applied, and we know that this is applied force, so this is an external. Does that mean the mechanical energy is not conserved because there's external force? Okay, it all depends on where you are looking at. It's like what duration of time you are considering. What is the interest of your analysis? So if I let the time T1 be the time when the ball leaves my hand, the moment it leaves my hand, that's T1. I start counting time from that instance. Anything that happened before T1, I do not see, I do not care, I just don't care it. So it's like anything happened before T1, I will not consider. So let T1 be the ball just leaving my hand, not when I push it. Because if you let the time be the time when I push it, then the force is involved. The force is included in your analysis. Okay, that's why the time I let it be the moment just after it is lifted up. Okay, now that is T1, and until T2 is the time when it reaches maximum height. Okay, so we got T1, T2, and I only focus between these two durations. Anything outside of this time period, that is not irrelevant. That is irrelevant to my analysis. So meaning that this force, the force that I apply to push it up is not there. It is not in my interest of analysis. You can think of this like video trimmer. When you trim video, you select the duration you want, you trim it, and then you drop the rest. Only the one that stays here, right? So you can think of this as you are trimming this instant and this instant from reality. Okay, I'm trimming this from reality. So anything happen before and after is I'm blinded by it. Okay, I cannot see. I don't know what happened. I don't care. Okay, so meaning that the force is not involved here. No force. So this would look like the ball is initially moving. It has a certain mechanical energy and it is initially moving. The force is not there. Okay, so if the force is not there, then there's no external forces, right? No external forces. What is the only force acting on this ball is mg. Mg, is there any other force? Mg is not an external force as discussed. Mg is a conservative, so no change in the mechanical energy. Mechanical energy, whatever the number here, is the same as mechanical energy up here, because I'm considering this T1 and this T2. If you consider the force, pushing force, that would be different. That's a different case. Okay, so here, from here to here, I know mechanical energy, same. So I can use the formula, half mv squared equals to mgh. Whatever the kinetic energy here changes to here. Because mechanical energy is conserved, so I can write Ke, whatever the Ke loss, it goes to the Pe gain. Okay, so cut out. I have half v squared. Okay, we put in the v, that's 30 square equals to 9.81 and then h. Okay, so calculate this. I get h equals to 45.87. And then here, look at the equation. How many significant figures do I put? This one, 30. This one is 3, 2, 3. This one can be 1 or 2. Can be 1 significant figure or 2 significant figures. If it's exactly 30, then it's 2 significant figures, right? So I'll just stick to the least number of significant figures. So I'll put 46 meter. Okay. Now, this one, your answer, when you change to 2 significant figure, this one is 2 significant figures. The answer before it, you write down better, because sometimes when you need to use this value to calculate another value, let's say you need this height to calculate other work done or anything, you use the value with the previous one, not this one, and not the 46. You use this one. Okay, if you use the 46, then you will get slowly deviate from the actual answer number. Okay, so it helps to write down the calculated value, and then you start another line that you change to the significant figure. Okay, so from here, I already got the h, right? So 46, that's A. B, okay, find its speed when it is 10 meter above ground level. 10 meter above, so I know that the maximum height reach is 46 meter. So I want only until halfway. That's 10 meter above ground. So again, back to the conservation of mechanical energy. I know that mechanical energy is conserved. So take 2 points, point A, point B. PE plus KE at A is equal to PE plus KE at B. Okay, so at B, calculate what is the PE. PE equals to MGH, so equals to 50, change it to kg. Okay, 4.905 joule. At B, what is the KE? Half mv square. So half 50 times 10 minus 3. The V we don't know, right? We want to find the V, so I just leave it V squared. Okay, this is the potential and kinetic at B. So the mechanical at B, that would be 4.905 plus, okay, this one we solve this. Okay, this one is 0.025 V squared. Okay, so 4.905 plus 0.025 V squared. That is my ME at point B. At point A, at the start, what is the KE? KE equals to half mv squared. What is this V? This V is the V that I give it, right? I throw it, I give it this V that's 30. So half 50 times 10 minus 3 times into 30 squared. That's 22.5 joule. Is that PE at the start? No PE. Okay, 0. So the mechanical energy at A is 22.5 joule. Okay, now this two, same, so 4.905 plus 0.025 equals to 22.5. Okay, just find V. So you get let's say we put it two significant figures, so ms minus 1, 27 meter per second at halfway, point B. Be careful you don't use the half mv square equals to mgh for A to B. It's not the same for this one, because if you take A to B, the amount of, what is this mgh? This mgh is the PE gain, right? PE gain, and this is the KE loss. So the velocity is not the answer here. Okay, this one we can use the two extreme points A, B. From here, if you go all the way to the top, then you can use this half mv squared equals to mgh. All right, okay, you can take this down. Take this down, and then we will have a 3-minute break, and we will come back and continue the rest. So we will continue in 8:05. Okay, let's continue. Okay, last one, the C. Give one assumption that you have used in your calculation. So in all the calculation here, they are based on one principle, that is the conservation of mechanical. So what is the assumption? That there is no external force. No friction, no external force. That is our assumption. Okay, let's go to the next example, one more. Example 4. A car of mass 800 kg is at rest on a road incline at 2 to the horizontal. Later, it is 100 m further up, traveling at 10 meters per second. Okay, so it started here, initial position, and it got up here. Now the velocity is 10 meters per second. Started at rest, right? So u is 0. This distance that it moves is slanted, okay, not vertical, slanted. So assuming there are no frictional resistances to motion, find the average driving force exerted by the car's engine. Okay, now what we want to find the force exerted by the engine, right? That is from the work done. We can take work done equals to force into displacement. This force is the one I want to find. So first I have to find the work done. Now, let's recall back what we have discussed. Just now we talked about work external can create what? External work can increase the mechanical energy, correct? Okay. So, is there any external forces here? We are taking from here, initial position to final position. What are the forces acting? We got mg. So we already know that mg is not external. What else? No resistance. So only one more. That is the engine, right? F engine. Engine force is an external. So the moment the engine force acts, the mechanical energy will increase overall. So this external force in this case is only the engine force. It is the only force, so it becomes the net. Okay, if you have another forces, then you have to minus it to find the net. So the net force or the net work done by the engine is equal to the change in the mechanical energy. So what we want to find is we want to find the change in mechanical energy, then we can find the Fe. Okay, so to find the change in mechanical energy, I take 2 points, initial position and final position. Okay, let's start with initial position. Now, initial position, mechanical energy, so I do Ke. Initially, it is at rest, right? So Ke is 0 joule, and then Pe. Now, what is the Pe? The Pe, we can take the reference line at the initial position so that the Pe is 0. Why do we do this? It's because the reference line is up to us. We can take any reference line I want because all we are interested in is just to get the change in the potential energy. Okay, so here 0, and then it got up here. What is the change in the potential energy? That is what I'm interested in. So it doesn't really matter where is the reference point. Okay, so to simplify my working, I will move the reference point or the ground 0 at the initial position so that the Pe is 0 here. Okay, so I just calculate the change in the Pe when it got up to the final position. So the PE is 0 joule. Okay, so any line, this reference line shows that 0 PE. Okay, let's stop for 10 seconds because I see the pop up saying that the internet connection is lagging. So 10 seconds. Okay. Should be okay now. Huh? So let's continue. Initial position, KEPE 0, 0. So ME, mechanical energy is 0. Now, calculate the mechanical energy at final position. Okay, final position, okay, let's start with PE equals to mgh. Okay, mg, so 800 into 9.81 into, what is the hash? Okay, somebody said cannot hear. Okay, the rest, how about the rest? Can you guys hear me? Are you guys still following? Still following. Okay, who's not follow? Who's still following? Let me know. I'll give you a thumbs up lah. You just give me a thumbs up. Shannon is joining. Okay, Shannon, can you hear? Is it good now?
Yes, already.
Yeah.
Thanks, teacher.
All right. Okay, yeah. Okay, so let's continue. I just repeat very quick here. I got the initial position ME 0, and now I'm calculating the final position mechanical energy. Okay, because I want to get the change in mechanical energy to find the work done. Okay, so PE mgh 800 times 9.81, and then this higher is vertical height, right? Vertical height, but this 100 meter is the sloping one. So you have to resolve it. We have it like this. Here is 2, is 100. So what is this height? This is 100 sine 2. Okay, this is the vertical height. So times 100 sine 2 equals, okay, calculate this, and I get 27389.125. Okay, so let's put it as 27389 for simplicity. Okay, so 27389. Now KE equals to half m and then v squared at final position, right? So it is traveling at 10 meters per second. So this is 10 squared equals to 40,000 joule. So total ME is 27389 plus 40,000. That's 67389 joule. Okay, now we got the ME at initial position, and find out what is the change. So you just take this minus this. So it's minus 0 is the same. So 67389 is the change in mechanical energy. Okay, because we have got an external force, so it increased the total mechanical energy to 67389. Okay, so I can write my work done by external force equals to 67389. And this external work done, there's only one external force, so I change this to F engine times distance equals to 67389. Okay, now this force S, what is this? This is not the vertical height, this is the 100 meter. Okay, because the force engine is sloping, and for it to do work, the distance must be in the line, right? So this is the 100, we take this sloping distance. So this S is 100. So FE equals to 67389 divided by 100. Okay, so you get 673.89. Let's round it off to 674 Newton. That is the force applied by the engine. Okay, so two examples. The previous one, the one we discussed earlier, example 2, it is the conservation of mechanical energy. We are solving it using the conservation of mechanical. This example, we cannot solve it using the conservation of mechanical energy because mechanical energy is not conserved in this situation. There's net force, external. So we have to solve it using the work energy relationship that is can be simplified in this expression. Okay, any net work external will cause mechanical energy change. Now, let's say I modify a bit the question. Let's say we have friction. Okay, we have friction. So we have a friction of 200 Newton. And we want to find the force exerted by engine. So if there is friction, then you got another external force, correct? Because friction is external, the engine is also external. So you got two external forces here. The two external forces, you find the net. The net will be the increase in mechanical energy. So I can change my equation like this. W external equals to change in mechanical energy. And this one, W external means that I take the force engine, I take work done by the engine minus work done by the friction. Work done by engine is sloping up. Work done by friction is sloping down. That is negative work, right? So we take the work up minus the negative work. So we can say that the engine is doing work against the friction, and that equals to the increase in the mechanical energy. Still, there is net external force. So this is the net external force. So when there's net external, always there will be change in mechanical. So we write this into, okay, WE equals to change in mechanical plus WF. And I just put in the values. FE times, this is 100, right? The change in mechanical energy, same, same. So 67389, and then plus the work by friction. So 200 times into the same distance moved, 100, equals, okay, solve it, and then we get this one is 873.89 equals to 874 Newton. Okay, so here is an example of if friction is present. So we calculate the same way, just that we add, we minus, okay, we minus the work done against the friction. work done against friction is going to be equals to the increase in total kinetic energy. Okay. In the next lesson, we will do past years, a lot of past years on the energy. Take a rest, and I will send you some exercises. Okay, I sent you 2 worksheets. This one you don't need to submit lah. You can just do it. I'll send you the solution answers. You can refer. Okay, so we have about half an hour. You can take the time to do practice, and if you need help, let me know in the chat. Yeah. Okay, just to clarify something. Just now somebody asked, which is a good question, if the car is moving at constant velocity. If the car is moving at constant velocity, does that mean no work is done? Because work, based on the work energy concept, right? Work is change in kinetic energy, right? So if the car is moving at constant velocity, no change in kinetic energy, does it mean that no work is done? Okay. Now, the thing is, you have to understand, right? So for it to move at constant velocity, the engine applied the force. The engine is doing work, right? It's doing the positive work because force same direction as displacement. The drag is doing negative work. So work is done. Yes, the work is done and energy is being converted. Whenever work is done, energy is being transformed, right? So when the engine do positive work, the engine adds the kinetic energy into the car. And when the drag do negative work, it takes away the kinetic energy from the car and then it changes it to other form of energy. It could be heat, it could be sound. So there's energy conversion, right? So where does the energy conversion go? From the engine, right? The engine is the working mechanical, or you can say chemical to kinetic, and then eventually it goes to heat, or it goes to sound. So there is energy conversion happening. Yes, there is a series of work done. This one is doing positive work, that one is doing negative work. Okay, but the overall, the net effect result that the car does not gain any kinetic energy. So meaning that we are only looking at this middle part. Okay, but you have to understand the whole picture is that there is energy conversion happening, right? It goes from here, it goes from here. So there is work done. There is work done, just that the energy is being taken away. Okay, it's being taken away out of the car so that there's no change in kinetic energy. Because this energy concept focuses only on one body, one particle body. We have not considered where does the energy go. We just focus on this body. Okay, just this body. That's why sometimes there's a little bit of confusion. Yeah, I understand that. Okay, so yeah, so that's the thing. So answer is there is work done. Yes, there's work done. Just that the kinetic energy is not no changes because it has been converted to other form of energy.